Hi everybody. We have just completed our midterm exams, which means that we have completed chapters 11 through 14 in the Beer and Johnson textbook. So today we're going to begin the second half of the material, chapter 15. And we are going to be covering chapters 15 through 19 in the second half of the class. The amount of material that we'll cover in chapter 17 is still up for debate, but I've posted a rough schedule for all of the chapters up through the end of our semester. So the one thing that I do want you to notice, if anybody's working ahead, we will not cover any information in chapter 18 at all. So just to let you know. So for today, we're going to start chapter 15. There are a total of 7 sections in chapter 15. We will omit section 6 and section 7 from our discussion. So we'll spend the next 5 lecture periods talking about the first 5 sections of chapter 15. I've also posted the PowerPoints, and just for reference, I think I'm going to attempt to put which slides go with which lecture and which section. So today we're going to talk about section 15.1, which coincides with PowerPoints 1 through 11 on the presentation. And I have also posted 3 problems that you'll be doing for homework. And I will attempt to do 2 problems. I'll attempt to do I don't mean I'll attempt, I can do them. That sounded ridiculous. I mean, if I have time, I will work out problem 15.2 and 15.14 on today's lecture. But we'll see how we go for time. All right, so having said all that, do you guys have any questions for me? So let's just take it away. Let's pull up the PowerPoints for 15 and start talking about the kinematics of rigid bodies. All right, now if you recall, in the past, we were talking about the kinetics and kinematics of particles. And today we're extending our conversation to talk about rigid bodies. And so the process is the same, where we covered a chapter on the kinematics of particles and then a chapter on the kinetics of particles. So now chapter 15 and 16 parallel that, except for 15 is the kinematics of rigid bodies, and 16 is the kinetics of rigid bodies. So what is the big difference? Well, regardless of whether we called something a train car or a wheel or a car going around a curve, we always talked about things as though they were points or particles. In other words, we didn't take into account the size and the shape, and if that would actually rotate. So a particle really can't rotate because, quite honestly, how would you tell, right? The other part is rigid bodies, which dynamics and statics are almost entirely concerned with rigid bodies. In other words, the body itself will not deform or break. It just stays the same shape and size, although it moves through space. So on this first slide, we talk about what we are describing, and one of the things that I love about the kinematics of rigid bodies in this textbook is that they draw rigid bodies, the general rigid body, to look sort of like a blob or a potato, and I can actually do that drawing. So this is a big deal for me. But we talk about, when we talked about particles, we could only really talk about a translation. So in other words, the first blob here, the first potato, shows that if you start with point A, and point A moves in a line, point B will move in a parallel line to that. And even if we follow some sort of a curvy path, if A follows a curvy path, B will follow a curvy path. That motion describes a translation. Now, if the body rotates, which we've done here, we take like I always say, this is like a skewer. Like you're going to put your potato on the barbecue grill, or maybe this is a chicken or a turkey breast or something like that, and it's rotating above the barbecue grill. A point A as it rotates, point B will rotate with the same sort of a motion. So this is pure translation. This is pure rotation. And the next picture shows I should say not just pure rotation, it's rotation about a fixed axis. The axis isn't moving. When the axis start moving, things get interesting in a big hurry. And by interesting, I mean very difficult to deal with mathematically. The third problem shows a general plane motion where we have some sort of this is like a bar on a slider block. And we have one slider block that's vertical in a vertical plane and one that is in the horizontal plane. And basically what happens is this moves down, this moves over. So there's either, you can think about it as being two translations or a translation with a rotation about a particular point. So you can think about adding one translation to one rotation, which is really the easier way to break the math down on that. And then the last, a spinning top, governs general plane motion, where if the top remained purely vertical, it would be rotation about a fixed axis. But the spin actually causes that point of the top to move around, and then the top also wobbles on the point. So that's a really, really generalized motion, not in a plane, but a generalized three-dimensional motion. So what we're going to talk about today is, I got to bring back my thumbnails. What we're going to talk about today is the idea of a translation with a rotation, and we're going to extend our conversation about kinematics, or in other words, position, velocity, and acceleration, to include both translational properties and rotational properties. So the first one, we start talking about a translation. If we have a rigid body and we look at points A and points B on that rigid body, if we reference them to a fixed reference frame from, in this case, point O, we can see that the position of point B can be thought of as the position of point A plus the vector that describes the relative position of point B with respect to A. And that we can differentiate those and find out that the velocity of any particle in pure translation is the same. So all that's really saying is that you have 2 points on a blob and it's not rotating, it's just moving in a particular direction, that the velocity of those 2 points is going to be the same. And when we differentiate a second time, that is also true for the acceleration. So whether the potato is moving in a straight line or it's moving in any sort of motion, in three-dimensional motion, that relationship is going to be the same as long as the motion is a translation. Now, there are some similar things, and this is the new piece that we're going to bring together, but there are some similar analogies that we can build on for a rotation about a fixed axis. So once again, this is the potato on a skewer being rotated on your rotisserie on your barbecue grill. So basically, if you take some point P, this axis A prime would be the skewer or the rotisserie knife, whatever you want to call it. And if you have a point P, it's going to actually describe a circle as the blob moves around that axis. Okay? So if we want to think about the velocity vector, and then in just a moment we're going to think about the acceleration vector, we can start by taking the arc length that P moves through on that circle and describe it based on the radius and the angle that it subtends as it moves through that rotation or part of a rotation. Differentiate ds dt and come up with a limit that expresses velocity. So you can find the same result by saying that the velocity is equal to dr dt, where r is that vector. It's not the radius of the circle, I want to be really clear on. It's the position vector of point O to point P. So velocity being dr dt can also be described as a cross product, which is omega crossed with r. And omega is called the angular velocity. So what we are talking about with the variable omega is that omega is the angle that the point moves through per time. And the angle is measured in radians. So omega has dimensions of time to the -1, because radians are basically a dimensionless quantity because it's a circumference divided by a radius, which comes out to be nothing, essentially. So it comes out to be dimensionless. So omega is equal to the angular velocity, and it is measured in radians per second, which is just called a per second. Now, I want to point something out here. If you look at this first picture, you'll see that the axis of rotation, AA prime, it coincides with the z-axis. So what that means is that all of the motion of point P occurs in a plane that would be the xy plane. It's a little strange to look at because it's tilted from purely vertical, but it's making a case that basically the motion is going to occur perpendicularly to the axis of rotation, and all of the rotation is a vector in the direction of the axis of rotation. Now, we could have defined z as being straight up and x and y as being in that horizontal plane. And if we did that, our math is going to get kind of messy in a hurry. So if you can keep the axis of rotation oriented toward one of the coordinate axes, the math just stays as simple as possible. The other thing, I'm not really sure if this is entirely clear, but when it says omega as a vector is equal to omega k, I would like to see that k bolded. What it's basically just talking about is the k unit vector, or the unit vector in the z direction. All right. They also point out that that is equal to omega dot. Okay, omega dot is just the rate of change of the angle per time. So we're just talking about the rotational piece here. And as you can probably imagine, we're going to add those two pieces together when we start talking about a more general type of motion. All right. So a little bit more math involved in that. We have that our acceleration is going to equal dv dt, and we've decided that v is equal to omega cross r. So we can do that cross product. And when we do the cross product, we have to use the rules of vector math, and we come up with sort of like a distributed sum where which is going to be measured in dimensions of length per time, is going to have two components. We have a dw dt, or d omega dt, which represents the change in the velocity, angular velocity, crossed with r, which once again is that position vector, plus omega crossed with v. All right? And this term, d omega dt, because it's in terms of radians per second, or radians per time squared, I guess would be the better way to put it, is equal to alpha, which is an angular acceleration. So alpha and omega are built upon the ideas. Alpha is built upon the idea of A, or linear acceleration. Omega is built upon the idea of V, or linear velocity. And both of them are functions of the time rate of change, either the first or second derivative of theta with respect to time. So we sort of have three variables that we need to consider thinking about all the time: theta, omega, and alpha. I'm not putting it up there right now. I'm just writing it down to remind myself so that I don't forget to talk about it a little bit later. All right. Well, if you recall when we talked about normal and tangential coordinates, when we talked about sort of relative coordinates with kinematics of particles, we divided up the acceleration into two components, a normal and a tangential, where the tangential represented all of the change of speed and the normal represented all of the change of direction. So we sort of do the same thing here, where we break up acceleration into a tangential coordinate and a radial coordinate. Now, if you look at this, if you think about it, we have alpha cross r is the tangential. Alpha is the rate of change of the angular velocity with respect to time. So once again, that tangential represents all of the change of angular speed, doesn't it? The other component, omega cross r, omega can be constant, and you can still have an acceleration in the direction of the radius. So that kind of makes sense, doesn't it? So the analogy is just what I was trying to point out in that way. All right. So if we take this, and once again, as much as I love to draw a potato, I love to draw a slab even more. So basically what this is, you've got that potato, and we're just slicing it. We're just taking a slice of the potato as it moves in the XY plane. So if you take this slide, and you look at this two-dimensional slab, it relates, if this is the z-axis, this circle that P is on is actually the XY plane. So what we've done is we've just taken a knife and cut right through it on the XY plane, and then we've straightened it back out again and put it in the plane of the slide. Okay? So because if all of the motion takes place in the XY plane, we know that all of our acceleration is going to be in the all of our rotational acceleration, all of our alpha, is going to be directed straight out or straight into the board. And since everything is cross products, it's going to follow the right-hand rules. So this slide is sort of where the rubber hits the road in terms of computation. So what we have here, instead of drawing a circle in 3 dimensions, we just have that vector r, which goes from 0 to p. And of course, as we rotate, the position p is going to change. But as we rotate, it's going to describe a circle in the XY plane. So the velocity then is going to be omega crossed with r. Once again, there's that funny omega k. I would rather see that bolded or subscripted, but there it is. And the magnitude of that, so you notice this is v with a vector symbol. This is just v. So this is the magnitude. The magnitude of the velocity, otherwise known as the speed, is r times omega. So r is going to be measured in dimensions of length, omega per time, or radians per second, or radians per whatever. So velocity then is going to be in dimensions of length per time, which is an awesome unit, an awesome dimension for velocity. Similarly, the acceleration is going to be that combination of alpha cross r and omega cross r. So we know that alpha is in the k direction, r, and we know that omega is the same, so we can just refer to that as omega squared. So right down here at the bottom are the components that become very interesting to us. This side, alpha, or excuse me, not alpha, a, just plain old a, in the tangential direction is written as the vector alpha crossed r. And the acceleration in the normal direction is written as the negative, because when you do that, it's actually going to be going into the board, and it's always going to be in the z direction. So tangential acceleration is always in the xy plane. Normal is in the z plane. And doing this vector analysis will help when we don't have just perfectly flush coordinates as well. But it's negative because it's directed inward. Right? And when we think about it being directed inward, if you think about the direction, it's just always going to be a negative to that. But the magnitudes of them are given over here. This is just r times alpha, and this is just r times omega squared. So the first column indicates the vector form. Second column indicates the scalar form. All right. So the equations defining the rotation of a rigid body about a fixed axis. What we have down here is a derivation for the kinematic equations based on a rotation. We have analogous equations for kinematic equations for translational motion. For example, we have omega is equal to omega 0 plus alpha t. You remember that when we're talking about a translation, we would have V is equal to V0 plus AT. So they're very similar. The form of the equations is the same. So we have an equation for omega, the angular velocity, theta, the angle subtended, omega squared, once again, which is just that analogy based on alpha and theta. So we eliminate time from that equation. All right, so what does all this mean for us? Well, what it means is we can work a whole new class of problems that have to do with rotations or translations and rotations. In other words, we can take into account the shape and the size of a body. So sample problem 5.1, we have this cable, C, right here, which has a constant acceleration of 9 inches per second squared, and an initial velocity of 12 inches per second, both directed to the right. So point C is moving toward the right with that velocity initially and an acceleration. We want to determine the number of revolutions of the pulley in 2 seconds. All right, so what we're really looking for when we're talking about revolutions is a theta, isn't it? We're talking about, and when you have 2 pi, when theta is equal to 2 pi, that's 1 full revolution. The velocity and the change in position of load B after 2 seconds. Well, we're going to have to assume that B keeps moving straight up, I would think, because otherwise this would be a much more complicated problem. And the acceleration of point D, which is right here on the rim of the inner pulley at t is equal to 0 seconds. All right, so we have to make a couple of assumptions. One of them is that this belt or cable is not going to slip, right? It's pulling that inner pulley. And then the outer pulley is going around with the same rotational properties, isn't it? Now, obviously, the translational properties of anything on the outside pulley are going to be different because we have a different size. We have a 3-inch inner pulley and a 5-inch outer pulley. And so that's sort of the construction of that problem. All right. So when we talk about this, then we get our velocities. We have our velocity and our acceleration. And then to determine what our angular velocity and angular acceleration are, we can just use that idea. Since we're in a plane, that the velocity is just the magnitude of the velocity is equal to r omega. Now, the important thing to notice is that once we get the omega for the inner wheel, the omega for the outer wheel is going to be the same. And so we can use that to come up with something about how many radians we're going to spin through on the outer pulley, and then we can convert that using those same equations into a linear velocity and a linear distance. So in other words, we can use this bottom equation, r theta is equal to some distance, in order to determine how far up B goes. So I really like this problem because it really makes that distinction clear between the angular and the linear, and then you have to use a little bit of analysis in order to realize that although the translational speed of the inner pulley and the outer pulley are different, the rotational speed and the rotational properties are going to be the same. They're going to turn through the same number of angles. They're going to have the same angular velocity and the same angular acceleration. And yet they're linearly different because of that radius. All right? And then we're just going to continue with that, evaluate the initial tangential and normal accelerations. So we have r omega to find our the equivalent. Well, I don't know. I want to phrase this a little bit differently. We know that this point D is on the inner pulley, and C is being determined by the inner pulley. So their linear accelerations are going to be the same. So we can make that equation, and then we know that what we're talking about there is a tangential. All of the change in speed is accounted for on the tangent. When we are on the normal direction, we're going to have the r times omega 0. if it's initial. So then what we have are two components of acceleration that are perpendicular to each other, and we can determine the magnitude based on the Pythagorean theorem and the angle at which that acceleration occurs by using the triangle and the angles involved in making that triangle. So, do you guys have any questions at this point? Okay. All right. So, having said that, let's work a couple of problems. And I still have 20 minutes. So I'm going to go over to the document cam, and we're going to keep these properties, we're going to keep these separate from each other. Okay, the problem that I would like to work is problem 5.2, right in between 5.1 and 5.3. And that's because it's quite similar to those problems. So in 5.2, we have the motion of an oscillating flywheel. That means it's going to kind of go back and forth. Is defined by this relationship. Theta is equal to this. Is expressed in radians and seconds. We know theta 0. We want to determine the angular coordinate. That would be theta, and the angular velocity omega, and the angular acceleration alpha when t is 0 and t is 0.125 seconds. All right. Now, one of the things that's really interesting about flywheels from an application point of view is a lot of things that need to store energy, especially angular energy, will use a flywheel. They have extremely high masses, and so they're slow to spin up, but they're slow to spin down. So especially in big, heavy machinery, you see a lot of flywheels, but there are also flywheels in your car and all kinds of other places. So they're kind of interesting. And they're sort of a classical engineering solution to a lot of different kinds of problems. All right. So in this problem, what we're given is an equation for theta, which is theta, I'm just going to write the whole thing out, theta 0, e to the minus 3 pi t, yes, times the cosine of 4 pi t. All right, so the first thing we know is that omega is equal to theta dot, and alpha is equal to theta dot dot, right? So that means that what's left to us really is to differentiate these equations. Let's also do this. I'm going to say d theta dt, use a different notation, and this is going to be equal to d omega dt, okay? So there we go. Now the other thing that we are told in this problem is that theta 0 is 0.5. So we can just substitute in 0.5 there just to simplify that expression a little bit. So in order to find omega, we're going to want to take the first derivative of that expression with respect to time. All right, and that is going to involve us using the chain rule, isn't it? Okay, so it's I had to write it out because my make sure I did that correctly. Yeah, so cosine differentiates to minus sine. So last term over here is minus 4 pi t sine 4 pi t. I'm going to put this down here. That looks awkward. Okay, so that looks like that. And then the first, when we differentiate this, this constant comes out front, so we're going to have a minus 3 pi e to the minus 3 pi t, and that entire thing is going to be multiplied by this, 0.5. All right, so there's my expression for that. Now to do alpha, we're going to take the derivative of this with respect to time. So we still have that 0.5 out there, the way I've left it. Now this is going to come out of here, and it's going to be the constant here. We're going to multiply that together. It's going to be negative times negative, so it's positive 9 pi squared e to the minus 3 pi t. And then sine differentiates to cosine, not minus cosine. So this remains a negative. So we get 16 pi squared. Did I bring that t out? That was, yeah, that should come out. Hang on. I don't have this complete because I have to do that. So this is actually going to be 0.5 times negative 3 pi e to the minus 3 pi t cosine, right, 4 pi t. There we go. Because it's this times, it's the derivative of this times this. There we go. Minus 4 pi e to the minus 3 pi t times the derivative of this, which is the sine of 4 pi t. Okay, so I think I got that time. Minus 3 pi e to the minus 3 pi t times the cosine 4 pi t minus 4 pi e to the minus 3. Yep, okay, correct. So this was like my work. And I didn't pay attention to what I was doing there. All right, so we have to do the same thing where we're going to have to do that first times the derivative of the second, second times the derivative of the first. And when we do that, we come up with quite an expression. We get 9 pi squared e, right, and then we have to multiply that by this, which is the cosine of 4 pi t. Then we subtract from that four times 3 is 12. I don't even know what I started to do here. This is going to be plus 12 pi squared e to the minus 3 pi t times the sine of 4 pi t plus 12 pi squared e to the minus 3 pi t sine of 4 pi t. There's my minus 16. There we go. Minus 16 pi squared e to the minus 3 pi t times the cosine of 4 pi t. All right. So mercifully, some of these will come together. We can combine like terms, and alpha actually simplifies to 0.5 times 24 pi squared e to the minus 3 pi t sine of 4, yeah, times the sine of 4 pi t. That's my first term. Then 12, 16, and 1 becomes 7 pi squared e to that minus 3 pi t cosine 4 pi t. All right, so that's my expression for alpha. That's my expression for omega. So then at t is equal to 0, you can plug in 0, and you can find omega 0 and alpha 0. And what you find is that a lot of this stuff either goes away or goes to 1, which is kind of nice, right? And so it turns out, oh, and we need to find theta 0 as well, which we already know is 0.5 radians. Right? That was given in the problem. Omega, when you plug everything in, turns out to be minus 4.7 radians per second, and the initial alpha is negative 34.5 radians per second squared. Now it's equally valid to call this seconds to the minus 1. In other words, radians are truly dimensionless, so you can call that this. And this unit is sometimes referred to, I'm not going to get into that. I'm not going to say that today. Forget. So then this one would be 34.5 seconds to the minus 2. Either of these is equally as good. All right. Now the next one would be at t is equal to 0.125 seconds. All right. So what you have to go is to plug those back into these equations, but also start with that equation, right? So that means that theta at 0.125 seconds is going to be equal to 0.5 e to the minus 3 pi times 0.125 times the cosine of 4 pi times 0.125, right? And when you plug that in, what you will find is that actually, this is actually 0.125 times 4 is 0.5. So that's half pi, so this actually goes to 0. So that means since it's oscillating the omega, the position at 0.125 seconds is equal to 0. So in other words, that pulley goes forward and then backward, and at 0.125 seconds it's equal to 0. All right, now that doesn't mean that omega or alpha are equal to 0, so you have to run through the math, but plug back in 0.125, 0.125, and you come out with negative 1.9 radians per second and a positive 36.5 radians per second squared. Okay, similar. All right. Okay, do you guys have any questions about that? All right. Now the next problem, I've only got 7 minutes, so I'm probably not going to get through this, but I want to at least set up 1514 for you. And when you do 1514, it's going to look very similar to the homework problem 1513 or 1515. I think 1515 is the one that you're assigned. Okay, so what we have here on 1514, we have this circular plate, and the radius is 120 millimeters. And it is supported by 2 bearings at A and B. Okay, so the plate rotates about the rod joining A and B with a constant angular velocity of 26 radians per second. Okay, that means omega is constant, alpha is 0. It also means that you would be really, really, you can think about this in 3 dimensions, and if we set this up in vector form, we're going to do I, J, and K for everything, and then it's going to be a cross product. If it were, the other way you could set it up is to consider this your z-axis and have everything rotate around it. I don't know. The problem leads you to use actual cross products and the math involved. So I think we'll go ahead and do that. But anyway, knowing that at the instant considered, the velocity of point C right here is directed to the right. That means it's purely x. If we're going to use this, if we're going to use x, y, z Cartesian coordinates, determine the velocity and acceleration of point E. All right. So that's kind of a strange problem, and whenever I have a strange problem, I don't mean strange as in, whenever I have something novel, my advice to you is to trust the math, okay? If you're not able, or if you're just not confident, or if you haven't done these kind of problems enough to visualize it fully, I would always say go with the math, all right? So if we consider that, the first thing is our axis of rotation, A to B. The axis of rotation. All right. So the first thing you can do is set up the coordinates for this. What you can see if we write this in vector form is that, and I'm leaning on the picture, not on what I'm drawing here, but A to B have no dimension in the x direction. So in other words, that's a 0i. Then from, I guess I really should I do B to, if I want Z to come out of the board, I really want that to be B to A, because that makes everything Z positive, so that's going to work with my set of coordinates. Does that make sense? Because if I do it differently than that, this is what I'm saying. If you go back to this picture, if B to A and Z both come out of the board as positive, then my cross products are going to work, and if I have a negative, we're going to know that means into the board or to the left or down. Okay, so let's stick with that. So from B to A then, in the J direction, we are going down from 180 millimeters to 80 millimeters, so it's minus 100 J. And in the Z direction, we are coming out of the board. The radius of the plate is 120, so we're coming out of the board positive 240, because it's 120 and 120, because the plate is all the way around. So if the radius is 120, the diameter, I should just leave this up here if I can, the diameter, oops, let's see if I can do this. I'd like to get everything on this if I could. Okay, while I'm drawing anyway. Okay, so that's my A to B. Well, I'm going to have to get my lambda AB, which I can do. Now the next thing is, what does my vector omega looks like? Well, all the rotation is about that AB axis. So I know that the vector is going to equal the magnitude times lambda of BA. So once I find lambda of BA, I'm told that I have a constant angular velocity of 26 radians per second. So that's given in the problem. And so I can do that, and I'll come out with a vector expression for my omega in XYZ coordinates or IJK coordinates. All right, now the next thing I want to know, I can say that the question tells me the instant considered, the velocity of point C is directed to the right. So that's telling me that the velocity of point C is purely, this is not a negative, it's plus 0J plus 0K. Okay, so that's what we're getting at when we talk about that. But we don't actually know what that means at this point. But it's asking us then, what is the velocity and acceleration of point E? All right, well, if C is moving to the right and we're rotating purely about that axis, that means that we can think about the velocity of E, this is going to be expressed as a vector, as being omega crossed with the distance or the vector from E to A. Because A is the axis of rotation. And so if we just think about the rotation of point E about point A, and we know what this omega is going to be, which is going to be a vector, and then we can come up with this vector, we can do that cross product and find the velocity of E. And then if we do that, we can do the differentiation and find the acceleration. All right, so VE then, I'm just going to set this up, is going to be equal to the evaluation of this cross product, where this is going to be omega x, omega y, and omega z, and this is going to be that position vector in the x direction, in the y direction, and in the z direction. Okay, and then you can execute the cross product. And you'll come up with a velocity of E written as a vector. All right. Now, after we do that, in order to find the acceleration of point E, we have to think about this in terms of being that long vector equation, which is going to be alpha times that radius from E to A. So we can reuse that same vector right here. And then we can talk about what that means. This is actually, does it tell me that's 0? It does. It says that the angular velocity, since omega is constant, that means alpha is equal to 0. So this entire term is going to go to 0. And all we're left with for the second part is just omega cross R. All right. So we know what, and this is just be from E to A. Okay. Well, looky here. So we can just write this then as being omega crossed with the velocity of E. Right? Okay, so then you can do the same thing, set up that and come up with an expression for that as being I, J, and K. Okay, so those two problems give you two very different approaches. One of them is more, first of all, you can do it a little easier because it's very flat. Then this is all vectorized. Now, you could have done this the same way if you would have considered the axis of rotation as being the z direction. You could have done it the same way as we did problem number 2. I don't really know if there's a lot of advantage to that, but you can always break it down that way if you have a fixed axis of rotation. All right, do you guys have any questions at this point? All right, well, let's flip back over here then. All right, and so that's it for section 15.1. You have 3 homework problems, and please let me know what questions and problems you have in the next lecture. I'll post this as soon as it's processed, and then we'll start on section 15.2 on Wednesday. All right, have a great day.